Bernie Wu. I'm the VP of Strategic Partnerships for MemVerge, and I want to pick up kind of where Steve and Charles left off. They were talking about preemption and checkpointing, and I want to deep dive into that a little bit more for you guys because that is one of our core technologies in this MMAI architecture. And so the goal of this, we refer to our checkpointing as transparent checkpointing. And what we mean by that is the ability to either pause or preempt and relocate a running GPU workload without requiring any changes to the application or even having the application necessarily be aware of it. There are other types of platform schedulers that they don't do this. So this is a pioneering effort here to use this kind of transparent checkpointing technology in this kind of use case. Other schedulers will send maybe perhaps a preemption notice, but then the application either has to be checkpoint aware already, or it has to be refactored, or just face a cold restart situation. So what our goal is to handle any kind of application, whether it has checkpointing built in or not, and be able to restart it somewhere else, hot restart it somewhere else, or hibernate it and then restart it. This allows us to remove what we think is quite a bit of the friction in doing any kind of resource scheduling and resource management and scheduling between the platform layer operators and the users. And besides this basic scheduling stuff, there are other use cases we see that it can expand the benefits to platform engineering. So, for example, we mentioned graceful node maintenance or shutdowns. We detect, for example, a GPU overheating, we can preemptively evacuate that node using this transparent checkpointing technology. Another example is this elastic workload bin packing and optimization. So not only can we maybe pack workloads more densely into different nodes, but also we can coordinate with Kubernetes infrastructure for horizontal scaling, scaling up and scaling down, especially long-running jobs. So things like inferencing are going to be long-running services, and at some point they may be using lots of memory, at some point they may be using less memory. So this kind of checkpointing can also be used to more gracefully migrate things into scale-up, scale-down situations. And then also idle resource and spot instance reclamation. A lot of people are going to they're going to want to use low-cost spot instances. And as Steve mentioned earlier, we have the ability with our scheduler to borrow unallocated resources from other departments and things like that. But in addition to that, if somebody has already allocated it, but it's sitting these resources, but they're sitting idle, we could also use this kind of technology to detect there's something idle and then
Bernie,
yes.
It wasn't clear to me that with the checkpointing solution you had that you could actually change the size of the, let's call it the GPU partition that you're using. Let's say I checkpointed and over here, and I want to move it over here, but I'm going to use a smaller portion of a GPU.
Yeah.
Or a larger portion.
Yeah. Though these are some of these capabilities of elastically increasing and decreasing currently are on the CPU side of this checkpointing. This checkpointing technology is both a CPU and GPU technology. Over time, it'll be more elastic on the GPU side. So that part I'll explain in a minute. Yeah. Another point that was brought up earlier in this panel was that there are other types of checkpointing technology. So I wanted to contrast what we're doing at the infra level versus these what we call AI ML framework type of checkpointing technologies, which are really designed for the data scientist and the ML ops engineer. So as you probably know, PyTorch and TensorFlow have built-in checkpointing capabilities. And those are used mainly in the training side to save model parameters and optimizer states at specific epochs or batch intervals. And they can be used to restore the state of a training workload in case of some sort of failure of the infrastructure. But one of the primary use cases of these is actually for rolling back overtrained or overfitted models, and then also to facilitate hyperparameter tuning. The reason I'm bringing this up is because a lot of people get confused about our kind of checkpointing, which is going on at the platform engineering level versus this higher level type of checkpointing going on at more at the data scientist ML ops layer. And also these kinds of checkpoints are this kind of checkpointing is also used for model interchange, because there's enough metadata such that you can take a checkpoint on this kind of infrastructure and then move it over to a different infrastructure or even a different CPU GPU combination and fire it up there. So that kind of framework type of checkpointing is used for interchange. And one of the peculiarities of this approach, however, though, is that these checkpoints are framework specific, not platform specific, not optimal necessarily for platform engineers, and they're also user specific because they have to store their checkpoints in specific files and directories. And so, in a larger scale environment with multiple tenants, you can imagine this can get pretty chaotic. And in addition to these frameworks, there are some workflow pipeline tools out there that do have what I call checkpointing between the pipe segments are out there. And if you look at checkpointing in general with this kind of approach, because it generally has to be done on a periodic basis for every epoch or batches, the overhead is pretty significant. It can be up to 25% of the total runtime is spent doing checkpointing.
Bernie, is the purpose of this type of checkpointing, is it what you're talking about here? Is that optimization, or is that really disaster recovery?
Most of this is for the model training itself. So you don't want to overshoot. So you have these different training epochs. Right. You don't want to overfit the model. So you do want to roll it back. You also want to tweak all the hyperparameters. So the primary goal has been for the model itself, optimization. Right. But also as these models get bigger and bigger, people start worrying about fault tolerance, and this is one way to a certain degree to address fault tolerance as well. Mm-hmm. But it's really, again, it's these kinds of things are used at the ML ops data scientist level, but somebody running a much larger cloud native infrastructure underneath that, he can't really address problems down in his level. And that's where, going back to our kind of checkpointing, is where we've been spending a lot of time working on that innovation. That's what we call transparent checkpointing. That's really the target persona there would be the site reliability engineers and the platform engineers. And this is a technology that does memory snapshotting. So we're actually capturing the state of the machine, all the caches and sockets, and as well as the ephemeral files and things like that, and saving all that to a file system. And initially we developed this for CPUs, CPU-based workloads and compute instances. And we've been working on this for several years, but we've had actually products in production based on this for the last 2 years. We have another product line called Memory Machine Cloud, where we have been using this to checkpoint CPU instances, EC2 instances out in the cloud. And we've demonstrated this working on cloud, bare metal, container, and VM environments. And so we've been developing this, we've been working on optimization of its overhead. So there's techniques that we've developed to reduce the interruption time. So one of the problems is that when you're doing this checkpoint, you have to pause. We also have to pause the application and dump all the memory and the files and everything else. And that takes time. So we in some cases have been able to reduce it by over 100x, the interruption period we call, before we can resume production. Likewise, we were doing work to reduce the amount of storage consumed by these checkpoints. So the techniques we're using there are things like, and some of this is borrowed from the storage industry. There's like a notion of an incremental memory snapshot. There's data compression technologies. There's asynchronous checkpointing technology where we go to memory first and then destage asynchronously to a file system. So all these different techniques in combination can be used to drive down the overhead of checkpointing to make it viable for production. And also we've been working on integrating this checkpointing engine with various types of batch schedulers, and now more recently on Kubernetes. So and then the pivot toward GPUs began with a collaboration that started in the first half of 2023, where we started working with NVIDIA on doing this process level checkpointing, extending it to GPUs. So a lot of that work, quite honestly, had to be done by the NVIDIA side. So they have been making modifications of their CUDA driver to support checkpointing. And the first CUDA driver that was released that supported checkpointing was debuted in Q1 of last year, the 12.4 driver. And at the same time, we presented a poster at the GTC event last year where we talk about achieving K8s Kubernetes and public cloud operational efficiency using, for the first time, a transparent checkpoint and restore that works at the GPU level. And the way this is done is right now currently a two-stage process. Right now, the x-axis is time, and so there's two things that are checkpoint and restore, and the y-axis is the GPU, CPU, and storage. I know that's a little bit hard to read, but basically it's a two-stage process. You can see, first of all, we checkpoint the GPU and dump that memory into the CPU, and then we checkpoint the CPU, including the GPU memory that was just dumped in there, and then combined with the files, ephemeral files, and other objects, storage objects, dump all that into a checkpoint image and store it there. And then we rehydrate on the other side, just doing the reverse process.
And where does it gets stored locally?
It could be, yeah, whatever you call locally. Yeah, we would in Kubernetes we would store it on some sort of persistent volume claim. Yeah.
Storage.
Yeah, we put it on storage.
It's super storage.
Yeah.
Storage.
So this is not in contrast. This is not some sort of live migration. This is a checkpoint, store, and recover. So we can use this to hibernate low priority workloads for an indefinite period of time. Somebody goes home for work in the evening. We want to just hibernate this stuff, and then the next morning bring it back and resuscitate it.
And it reminded me of SRDF. Yeah. See.
Yeah. And then the way we implement this now in Kubernetes, just one more level of detail, is that we've built an operator. And this operator allows us to take advantage of all the automation benefits of being on the Kubernetes platform. And there's two basic ways that it can be deployed. One is as a custom resource device, CRD, and so we can deploy as a daemon set across a namespace, or we can also deploy as an annotation to a specific application. So we can annotate or be labeled to specific applications, and then we can be deployed as what's known as a Kubernetes sidecar. So there's two ways we can deploy. And then again, as to your question, we store all of our checkpoints into this persistent volume as shown on the right. And the beauty of this is that it really helps reduce what we call the friction of moving or hibernating stateful, long-running workloads, which are a lot of AI workloads are like that, or also long initiation time workloads. So a lot of workloads take a long time just to load up the model weights or just to get initiated. So this is also a useful
way.
Since
it's using Kubernetes, if Kubernetes recognizes, for example, an AMD MI card, would you be able to do the same thing with AMD?
Yeah, we plan to support AMD along the way. Yeah, absolutely, yeah. So we can use a similar mechanism for AMD. So what's ahead? Right now, there are going to be further performance enhancements and optimizations. As you saw, the initial work that we've done so far with NVIDIA is a two-stage process. We can parallelize that so that the memory dump and from the GPU and the CPU are occurring in parallel. There's also been a lot of talk about fractional and also multi-GPU node supports. Some of this work is going to be done in collaboration with NVIDIA because it does require further evolution of their CUDA driver to support that. Likewise, with cross-generational GPU migration, right now we're limited to like, as we mentioned earlier, A100 to A100, et cetera. So some of those constraints will be relaxed over time in our collaboration with NVIDIA. In addition, we're also working on what we call transparent clustering, clustered checkpointing. So right now we can do individual nodes, but as you know, a lot of things, especially on the training side, are clusters, and even inferencing is becoming a distributed architecture. So the notion of gang scheduling and be able to transparently checkpoint that is also on the way. So the notion of doing what we call job set, actually that's what Kubernetes would call it, job set coordination across multiple pods. And then also supporting these backend networks. There's RDMA networks, there's InfiniBand networks, NVLink networks, and some of that will be done in collaboration also with NVIDIA. This checkpoint technology has other use cases besides just this basic scheduling and platform engineering management. Hybrid cloud scheduling and migration is another use case. Heterogeneous pipelines. So a lot of these pipelines are going to be pieced together from different software components. You can imagine a multi-agentic LLM RAG pipeline could have several stages, and there could be situations where we want to checkpoint and migrate or hibernate the entire pipeline and then restart it somewhere else, or just let a higher priority work go by it. HPC is also a good application for this type of clustered checkpointing. And as mentioned earlier, model loading and model restart. So also kind of putting, kind of accelerating further, turbocharging further serverless architectures and things like that can be used with it, can be a beneficiary of this kind of technology. And also we will be working with other schedulers and more directly integrating our stuff into things like Slurm. So the next checkpoint for this checkpointing technology will be KubeCon in April. So this kind of gives you a clue where we're heading. As I said, we are working toward doing these cluster-wide checkpoints. And so it's been very exciting. We'll be presenting it jointly there with Microsoft. And again, to remind you, we have this Pioneer program open up for anybody that wants to be an early adopter of our AI infra. Thanks.
Stephen, I don't know if this is an appropriate question. My first time.
That's a terrible question.
I won't. So do you have any reference accounts yet, or any reference accounts you can talk about?
No, we're just starting this early adapter thing as we speak.
Okay.
Yeah.